Bismillahirrahmanirrahim. Assalamu alaikum warahmatullahi wabarakatuh, dear students. The third part of fifth lecture on biosynthesis of natural product with course code Chem 524. I am Dr. Shahid Amin. And this part of this lecture, we will be discussing some of the major biological events occurring in living organisms. And those major biological events that we have to discuss in this lecture, these include the construction mechanism for secondary metabolites. There will be an introduction to these construction mechanisms, that how the secondary metabolites are made actually, along with some specific examples. So let's see what we have to discuss in today's lecture. So this will include introduction to the construction mechanisms and a common construction mechanism for secondary metabolites, along with the discussion on first of these reactions, that is the alkylation reactions. The reference book that the students will be following, this is by Paul M. Duig, Medicinal Natural Products, a Biosynthetic Approach. This is third edition from 2009 by John Wiley and Sons. So first we have an introduction to the construction mechanisms. Natural products are biosynthesized, and this biosynthesis occurs by a sequence of reactions that are catalyzed by enzymes, and we know that enzymes are very efficient in their functioning. When the enzymes function during these biochemical reactions, enzymes also need some cofactors like NAD positive, PLP, coenzyme A, SH, some metal ions. So these are the coenzymes, cofactors that will be involved in the working of enzymes while carrying out the biochemical transformations during the synthesis of secondary metabolites. So the biochemical reactions, although these are very complex, and the involved enzymes, these are very complex structures, these are proteins, and they have very big structures along with their size. They are very complex, and there are some specific sites inside the structure of the enzyme that are actually responsible for carrying out the chemical reactions. But it will be very much difficult to express those biochemical reactions by taking into account the structure of the enzymes. So the biochemical reactions are expressed using established chemical principles and mechanisms that we discuss in case of the organic chemistry. So the chemical analogy is similar to those we discuss in case of organic reactions. These will be discussed throughout the course of this discussion. We know enzymatic transformations, these are very efficient and very rapid. They happen in a very short period of time, and the efficiency is very high, and the conditions that are required for enzymatic reaction, these are just mild conditions that happen at the physiological pH, that is the pH inside the bodies of the living organisms, in contrast to the organic reaction that we carry out in our chemistry labs, and these normally require very high temperatures and sometimes very strong bases or acids. But in case of enzymatic reactions, there is nothing like that. The conditions for these reactions to happen, these are mild conditions. So some of the reactions that are very important reactions, and they are encountered very frequently in the biosynthesis of secondary metabolites. These include, for example, the alkylation reactions, the Wagner-Mewine rearrangements, aldol and Claisen reactions, imine formation and the Mannich reaction, and transamination reactions, in addition to decarboxylation reactions, oxidations and reduction reactions, or redox reactions simply, phenolic oxidative coupling, halogenation reactions, and glycosylation reaction, that is the attachment of some sugar molecule, maybe glucose, fructose, or rhamnose, or some other sugar that will be going to be attached to the natural products. So these are some of the major reactions that we actually see in the biosynthesis of the natural products. First we discuss the alkylation reactions, how these reactions happen. Alkylation reactions are those reactions that involve the formation of the attachment of some alkyl group. This doesn't mean that this will be a simple alkyl group like simply always a methyl, ethyl, or propyl group. Rather, these may be some modified alkyl group. They these are known as alkylation because these are just similar to simple alkylation reactions. These may include the methylation reactions, but these are not confined just to simple alkyls like methyl, ethyl, etc. Rather, some complex or some complicated alkyl groups or the derived alkyl groups, these will be also involved. So alkylation can happen in two ways. The first way is nucleophilic substitution, and the second one is electrophilic substitution. So nucleophilic or electrophilic, any of these reactions, these may be happening while carrying out alkylation. There are two types of alkylating agents. These are two types of mechanisms, and these are two types of the alkylating agents that will be responsible for donating the alkyl groups. One of these, very important, this is S-adenosyl or adenosyl methionine, SAM or adometh. And this normally this provides with C1 units, that is a methyl or modified methyl. That is the derived methyl group or derivative or methyl group. And then the second one, this is dimethyl allyl diphosphate, DMAP, DMAPP. And this provides us with C5 units. So first we look at the alkylation reactions that happen via nucleophilic substitution reactions. The C5 methyl building units, this is supplied from 1-methionine and or 1-methionine and is introduced by a nucleophilic substitution reaction. And it's done in during the biosynthesis process by converting 1-methionine or 1-methionine into S-adenosyl methionine, that is SAM. And when it's converted to SAM, then it facilitates the SN2 type nucleophilic substitution reactions, because the group that is attached here, this will be a very good leaving group. So in a SN2 type reaction, this reaction very easily can happen. So this is the formation of SAM, how this is produced. Here we have L-methionine, and L-methionine structure, it's a amino acid actually, and it's sulfur-containing amino acid. We know with sulfur there are two lone pairs of electrons that are there, only one is shown here. So this reacts with ATP. ATP molecule has three parts. One is that is a nitrogenous base, that is adenine, and there is sugar and adenine combined together to make what is known as adenosine, and then there are three phosphate groups that are joined together by ester linkages. So this is ATP or adenosine triphosphate. Here this triphosphate is a very good leaving group, that is, it can leave in the form of phosphate, triphosphate ion, and this bond is highly polar because of high electronegativity difference between oxygen and carbon. So this oxygen is partial negative and this carbon is partial positive. In case of methionine, we have sulfur, and sulfur has a lone pair of electrons. So this has excess of electrons. This electron could be donated to any electron deficient species. And this molecule, this carbon is electron deficient because it has a partial positive charge. So this sulfur will attack this carbon, and the bond pair between oxygen and carbon, it will be shifted towards more electronegative atom, that is oxygen here. So this triphosphate, it will be acting as a leaving group, and this sulfur will be going to make a single covalent bond with this carbon. So as a result, we have structure like this. So this structure is known as SAM or S-adenosyl methionine. So this is an active form of methionine, we can say, because this sulfur now, it has a positive charge, and because of this positive charge, both of this carbon, all of the atoms that are directly attached to this sulfur, they will get partially positive because of the inductive effect of this positive charge. So the result will be that we'll be having all of these groups got polarized. Out of this group, because this group is very small group, so its ionization will be far more as compared to the other two carbons. So this carbon may take part in the following reaction. So this whole transformation is happening through SN2 reaction. And the enzyme here involved, this is SAM synthetase, that is enzyme that is responsible for the synthesis of this molecule. Now in the next process, O and N alkylation, it will happen by utilizing this activated methionine, that is SAM. So because both oxygen and nitrogen, they have lone pairs of electrons, so they are, we can say these are electron rich species, and this carbon is partially positive because of the inductive effect of positively charged sulfur. So as a result, these lone pairs, they may flow towards this carbon. As a result, there will be start of making of a covalent bond between this oxygen or nitrogen and this carbon. And once these electrons flow towards carbon, the bond that is already there between carbon and sulfur, it starts breaking, because the maximum capacity of this carbon to hold the total number of electrons, this is only 8. That is, it could make only 4 covalent bonds. So already it has got 3 covalent bonds with hydrogen, and 1 is already there with the sulfur. So when it starts making a bond with the oxygen, this bond will going to be broken. So as a result, we will be having a structure like because of this SN2 reaction again, and the enzyme involved here is methyltransferase. So as a result, this methyl will be attached to this oxygen, and this oxygen will acquire a positive charge because it has utilized this lone pair of electron to make a covalent bond with this carbon that will be coming towards this oxygen by losing its bonding pair towards sulfur. So as a result, this oxygen will be a positively charged species. It may lose this proton, and both of these electrons, they will flow towards oxygen. As a result, we will be having O-methylated product here. Now this O may be attached to any secondary metabolite, and so that way we will be having O-methylated secondary metabolite. Similarly, if there is oxygen, oxygen will get attached to a CH3 group. It may get attached to one CH3 group, or it may lose the other hydrogen also in order to get one more CH2 group. So what's the result? We are having O-alkylated products, and along with that we are having again SAH. This is not SAM because it doesn't contain the moiety that was coming from adenosine. So that was coming from so it's a SAH because it has lost one of its methyl group. So because of loss of that methyl group, it's now without that methyl. So instead of methyl, we'll be having hydrogen here. So this is SAH, S-adenosyl homocysteine. This molecule, it may go further in the presence of SAH hydrolase enzyme that will cause the hydrolysis of this this bond that is between sulfur and adenosine. So as a result, we will be having OH attached to adenosine that will be converted to simple adenosine, and this will be actually adenosinyl. So by attaching one OH from water, it will get converted to adenosine, and this sulfur will get one hydrogen. And this is the structure that we call as, this is demethylated methionine, and this is known as homocysteine. This homocysteine via another reaction that is catalyzed by methionine synthase, it will be converted to its methylated original product that is actually responsible for the methylation after reaction with the ATP and being converted to SAM. So again, we have here regenerated L-methionine. This is the way oxygens or nitrogen, they get methylated. Now, if we talk about the methylation at or alkylation at carbon position, that is the C-alkylation, the same reagent can take part in that reaction, but for that case there must be some activating group, like we are having here OH group. OH group may react this way and it will get converted to O-methylated product. are the group that is present, the carbon atom that is present immediate to this OH group, carbon containing this OH group, that is the vicinal carbon. So this gets activated because of the resonance effect of this OH group. This electron pair will be going towards this bond, and double bond will be created here. These two electrons, they will be moving towards this carbon, and this carbon will be having a negative charge. Both of these electrons, they will be concentrated upon this carbon, although it may move to other position like this para position or this meta position. We will be concerned here only with this ortho position. So this ortho position that becomes highly activated, this is a nucleophilic center, so it will be moving to the electron pair will be moving towards this carbon that is partially positive. So as a result, this methyl, it may get attached to this position. So we will be having, for example, this is a simple phenol or phenol. We will be having 2-methylphenol. Similarly, if we have two carbonyl groups in some molecule, and there is some CH2 group in between these two methyl groups, that CH2 will be active methylene, so it may lose its proton to some base, and this carbon becomes negative center, so this will be nucleophilic center. It may attack the CH3 group, as well as this CH3 will get attached to this position. So this is the way alkylation reaction happens through nucleophilic substitutions. Another way alkylation can happen, or another alkylating species, this is C5 donating species, as we talked before, and this is known as dimethyl allyl diphosphate. It will provide us with, it will provide the secondary metabolite with the C5 unit, or it may be used in the synthesis of the secondary metabolites. So the reason here is the reason that this group can act as an alkylating agent. It resides inside the diphosphate group that this molecule contains. Diphosphate group, like triphosphate, it's a very good leaving group. So this reaction, this reagent can donate its alkyl part. One difference from the previous reactions, this is that those reactions were happening through SN2 mechanism. This will be going to happen by SN1 mechanism. That is a two-step process. So here we see that if we talk about the O-alkylation using DMAP, then this is a structure of a DMAP. Here we have diphosphate group here. So this bond between oxygen and carbon, it gets broken because this will provide us with the, this diphosphate group. This diphosphate group is a good leaving group. So when it leaves, this carbon attains a positive charge. Now this molecule, or this species, not molecule, this is an ion. So this is in this ionization process that is produced, this is resonance stabilized. This electron pair, it may move here, and as a result this charge will be shifted because this electron pair, it will be moving here, and this carbon becomes electron deficient. It will be having a positive charge, and this structure overall, because this charge is resonating in this region, it may be shown this way along with a positive charge in the center. So we are having here this positive charge on this carbon as well as this carbon. So any electron donating species may attack here or here in order to make the O-alkylated or N-alkylated product. As we see here, for example, if OH that is contained inside the structure of any secondary metabolite, it attracts this carbon, so we will be having a species like this. Because of deprotonation, we will get this O-alkylated product. Similarly, if the reaction happens here, at this position, we will be having a product like this. So now we look at the alkylation reaction that happens through electrophilic additions. This occurs in case of the biosynthesis of terpenoids and steroids. Here, two or more C5 units, these are joined together utilizing carbocation chemistry by electrophilic addition of carbocation on alkenes. That are very common reactions in case of organic chemistry. Here, DMAP may ionize similar way we discussed in the previous slide, to generate a resonance stabilized allylic carbocation, which can then react with the alkene, like there is one example, the isopentenyl diphosphate IPP. It, as a result, we will be having a species like this one. So this is our carbocation that is produced as a result of ionization of DMAP. And this is our IPP, that is isopentenyl diphosphate. It's double bond may attack here because this is an electron-rich system. It contains pi electrons. So this pi electron may flow towards this carbon that has a deficiency of electron. So as a result, this carbon will get a positive charge because these electrons are moving towards this carbon. So this positive charge may be this may be eliminated by deprotonation reaction. In this way, for example, the carbon that is vicinal to this carbon, like this one or this one, they may lose one proton in order to get this positive charge stabilized. So here this carbon is losing one proton, so because of this deprotonation reaction, we have this product that is geranyl diphosphate. That is another actually alkylating agent that can go further for the alkylation reactions. Similarly, this positive charge may be eliminated by cyclic. It may its elimination of this positive charge may go towards formation of these cyclic products like this one. So if this structure it cyclizes this way, we will be getting a 6-member ring, and a positive charge will be here. That positive charge may be removed by reaction with some other species. So the initial carbocation that is generated by, as we've seen in the previous slide, this was generated by dephosphorylation reaction. That is, diphosphate group was being removed. In addition to that dephosphorylation that is happening by SM1 mechanism, this ionization may also be carried out, or the carbocation may be generated by protonation of an alkene or by protonation and ring opening of epoxides, as we can see here that this is some of the leaving group like diphosphate group. It may leave or some other group may be there, and as a result we will be having a positively because positive charge carbon, and this is a carbocation because both of these electrons will be going towards this leaving group. Similarly, if we have an alkene, if it gets protonated, then one of the carbon out of these two, and this will be having a positive charge. Similarly, if we have an epoxide, it gets protonated because oxygen has 2 lone pairs of electrons. These lone pairs of electrons may attack to attack this proton, and we will be having oxygen with a positive charge. Then an electron pair from the other bond, it will be shifted towards oxygen in order to that is discharging this oxygen. So as a result, we will be having a positive charge on that carbon. SAM, as we discussed in the alkylation, nucleophilic type alkylation reactions, these may also alkylate alkenes by an electrophilic addition mechanism, and they will be providing C1 unit and generating an intermediate carbocation, similar to as we have seen in case of this protonation reaction. For example, this is an alkene, it may attack this carbon. Again, the reason is because this carbon is partial positive. This is pi electron system, that is the electrons are loose, so they may flow towards this carbon. As a result, we will be having a carbocation. But this carbocation is generated not because of a protonation reaction, rather by the action of some alkylating species like SAM. Now, the carbocation that are produced during the reaction that we discussed previously in the previous slides, these may be discharged by deprotonation reaction this way. As a result, alkene will be formed. Similarly, this way, if deprotonation happens this way, then we'll be having a three-member ring formed, or uh, this may be done by acceptance of some electron donor species or some electrophilic type of reaction. For example, this water molecule may attack this carbon and followed by deprotonation. As a result, we'll be having an alcohol molecule.